Okay, we're going to work through a couple of titration problems where we are at the equivalence point. Being at the equivalence point is the most challenging of the titration problems. So we're going to work a couple of them. In this problem, it is asking us to titrate a weak base. In part A, it's pyradine, and I'm going to just call that B for weak base. And I am reacting it with a strong acid. Now, as a strong acid, I will get rid of the part of the anion that's neutral, and I will let H3O plus represent my strong acid. This is a one-way reaction. I will produce the conjugate acid of that weak base and water. This is a one-way reaction, so an ICF table will be appropriate, and I will want to plug moles in. Don't know where my M went. There you go. No, still don't see it. Moles. Okay, now I know the molarity and the volume of the pyradine, so let's figure out the moles that would be of the pyradine. So the number of moles of my weak base would be the molarity times the volume This molarity times volume will give me a moles of 0.159. And I will plug that into the table. Now, they didn't give me molarity and volume of the acid. They just gave me the molarity. But when they told me it was at the equivalence point, they are telling me that this number has to be the same. So I put the very same value here as here because that's what the definition of the equivalence point is. Before the reaction takes place, there's none of that, and I don't care about water. So I use up the least. The least is the same for both. Both of them are the same number, so I'm going to subtract those values and produce 0.159 of this. I've consumed those, and I now have 0.159, keeping in mind this is moles, of that weak acid. So this is a weak acid. We do not have a buffer because we don't have both the base and the acid. And every time you are at the equivalence point, you need to follow an ICF table with an ICE table. Every time. You have got to consider what this weak acid is doing in the presence of water. What it does is reestablish an equilibrium with its conjugate. Right now it says there's none of the base, but it can't stay that way. So the acid will donate its proton to the water and give me the base back plus H3O plus. So there is the weak acid reaction. I will keep in mind that this is a weak acid, and as such it has an equilibrium, and as such it has an ICE table, and as such we need to plug molarity into this table. Well, I don't know molarity. I do know, in order to get molarity, I'm going to have to figure out the total volume in there. Now right now I have 2.65 liters of the pyradine. That's what it says up here, 2.65 is an awful lot to titrate, but 2.65 liters of the pyradine. I need to know how many liters of this nitric acid is required to get that volume. To get the number of moles that we have here. So I know the moles of the nitric acid. I know the molarity of the nitric acid. And if I know the moles and I know the molarity, I can get the volume of nitric acid. So, to get the volume of the acid, I'm going to take the moles, 0.159 of the nitric acid. I don't want moles. I want volume of the nitric acid. The molarity is 0.447 moles per liter. And that is going to give me a value of 0.356 liters. Okay. Something's wrong. Oh, no, it's not. It's a much higher concentration. Sorry, I was doing a little mental math there. This is a much higher concentration for the acid than we started with for the base, so it won't take near the volume. So 356 milliliters or 0.356 liters does make sense. Now, what am I going to do with that number? I want you to keep in mind what we're trying to do. We need the molarity of this acid. We know the moles of this acid. We have to divide by the volume of the solution. I didn't know the volume. I have 2.65 liters of the base, and I have 0.356 liters of the acid, and when I add those two together, I will have, let's see, 60, why am I having a hard time? Yes, that's there. 0, 3. So there's the volume, the liters of that. So the concentration, the base, this acid concentration would be the moles, which I get out of the top table, of 0.159 moles. Let's look up here. I'll underline where I'm getting that from, of the acid, divided by the total volume, and that will give me a concentration of 0.0529. Okay, so now I can plug that into my table. 0.0529. Don't care about the water. Before the reaction takes place, these are 0. I use up some of this guy. I produce these. I'm left with 0.0529 minus x, and x, and x. Now what do I need here? I need the Ka for the conjugate acid. They didn't give me the Ka. I know the Kb. To get the Ka, I'll take 1.0 times 10 to the minus 14. That's Kw. And I will divide by 1.7 times 10 to the minus 9. That is the Kb value. And that is going to be equal to x squared over 0.0529 minus x. I won't show the algebra. I think by now you've seen the algebra of that many times. But this is going to give me an x of 5.6 times 10 to the minus 4. Good assumption. If I assumed x was small, it is small. I consider what x is. X is giving me the amount of H3O+. So if I take the negative log of this number, I will obtain the pH. And the pH is 3.25. So that's part A, going through and calculating the pH at the equivalence point between those two substances.